Okay, so we're going to start with example 3 and do 1 through. And it's on page 204. Now again, I'm going to do this with you both ways. I'll set it up to C with the C. You guys migrate towards the back again. Did everybody move up? You already did? Okay. Except for Sarah. Sarah, you're killing me. All right. In the survey, U.S. adults were asked to identify what devices they use to access social media. The results are shown in this figure on your tablet. So see the tablet on page 204? These are the results. 94% said they use their computer. 46% said they use their cell phone. 16% said tablet. 7 some player, etc., etc. Now, to me, that adds up to more than 100. How is that possible? How is that possible? They could do both. So this doesn't have to necessarily add up to 100. But when we do ours will add up to 1 because we're going to make it a probability distribution. So we're going to base it out of there. 7 workers are chosen at random and asked whether they use their cell phone to access social media. So cell phone is key right here. We're going to construct a probability distribution for the number of adults who responded yes. Now, there are multiple things down there. There are how many choices? 6 choices? 7? There's 7 choices. Is that a binomial experiment? If we give them 7 choices? Binomial means 2, right? If we give them 7 choices, does this make this a binomial experiment? No. But how did they word this in the wording so that we do have a binomial experiment? It's cell phone or not cell phone. Okay, so now they're only giving them 2 choices. Did you use a cell phone? Did you not use a cell phone? So even though there's a whole list of things, that's not what we're looking at. What we're looking at is the fact that they said, did you use your cell phone? So we're taking this information, and what is the percentage of people, according to that tablet, that use their cell phone? What percent use their cell phone? Look at that tablet thing. 46%. That's the people that said, yes, I use my cell phone. Okay? Everybody else, no. All of those other 6 categories are grouped into the no. So let's reset this into the no. So I do this by saying 1 minus 0.46, and I get 0.54. Now, I'm asking how many people? How many random people did I ask? You're going to have to look at the problem because I moved it up a little bit. I asked 7 people. So my trials is 7. My X variable, can 0 people say yes? Meaning they use their cell phone. No one uses their cell phone? Can 1 person say yes? So this is going 0, 1, 2, 3. This is all we mean by our variable X. So we're going to make this chart like this. All of the possible things. Is this a binomial experiment now? A binomial probability distribution. It qualifies. What are our 4 things that have to be there? Anybody remember them? Two what? 2 outcomes. Their answer was yes or no. Yes, cell phone? No, not cell phone. Okay. What was another thing that has to be? Good. Is my probability ever going to change? It's always going to be 46%. One is independent of the other. Okay? What's another one? But like kind of just said it. My trials are independent. Doesn't have any effect on the other. And the random variable x represents all possible answers, outcomes. Okay? The fact that it is a probability distribution is where the probability is 0 to 1 and the sum is 1. That's the separate part. This is the part that makes it a binomial. It has to qualify first to be a probability distribution, which we did. So now, to find your probabilities, you have two ways. You can use Bernoulli's. This is called Bernoulli's, what this say. You can use Bernoulli's, and you would set it up like this. It's a pattern. Don't worry about what the formula looks like. Do the pattern. 7 things, 0 at a time. I want none to be yeses. My success, always put your success rate first, then put your failure rate. So you want 0 successes, you want 7 minus 0, 7 to say no. You can put that in your calculator, or next time you do it, you can change this. You're going to change this one. If you like this, I always have 1 or 2 kids that absolutely still likes this. You're going to have to change this one and this one. And you're going to keep the pattern going. The other way is your calculator. You go to second pairs. You look for the word binomial PDF. It's a binomial. There's only 1, 2 words that say binomials if you scroll through this. This is a cumulative, and we'll talk about that later on. This is a probability distribution, is what we're building. See the word 3x? That stands for probability. I want the probability of that happening. So all I have to do, and you should be prompted like this. If you have the 83s, you're going to have to string the information, and I'll show you that in 1 second. So I have 7 trials. My probability of success, we always measure success. And I'm going to start it to 0. And I'm going to paste. Now, once you get this 3 decimal places, make sure you round. All you have to do to this one is second enter and change that 0 to 1. Then go back and change it to 2. Then go back and change it to 3. Now, if you have the 83s or you don't have the software, when you put this in, you have to string them out. But they're in alphabetical order. N, P, X. N is how many there are, so you got to do this. 7.460, your first time through. And then just second enter, second enter. The nice part about it, it's in alphabetical order. So it's easy to remember the order. So make sure you have a calculator handy and make sure you try this. Otherwise, you cannot complete this table. I don't care if you use the C. The C you have to change in 3 places. And that's fine too. If you guys like doing that, that works well. This step on the calculator is nice. So you should be able to fill this whole chart in no time. And when we do this, what should the sum be? 1. My probabilities should all be between 0 and 1. So if I get anything that has an E, I'll know that something's wrong because my probability cannot be greater than 1. I think the 7 might. I'm not sure. Nope, that one has a probability. They all have probabilities. But if you find one with an E, don't forget to move that decimal place. Don't give me something that's greater than 1. So I'll fill these in. Okay. Now the nice part about this is now when we ask for probability, you say, what is the probability that the person at random that I select, a random person, that I select will say, maybe I'll get at least out of my 7. You could do an exactly, you can do an at least at most. The probability that exactly out of my 7, that exactly 5 said yes. They used their cell phone. They used their cell phone. So when I want an exactly, I just come right to the 5. There's my probability. Okay. If you like to look at it as percentages, because it makes a little bit more sense, I have a 12.6% probability that exactly 5 will say yes out of my 7. If I say, what is the probability that at least 4 said yes? 4 said they used their cell phone? At least means that or greater than. So I come to my 4, my 5, my 6, my 7, and I add those up. This in itself is mutually exclusive. Each one of those boxes, it doesn't overlap. Unlike theirs, where theirs overlaps, ours does not. It's the probability of just them saying yes for their cell phone. It's always a little bit confusing because that one doesn't add up to 100, but this one has to add up to 100. So when we ask a probability now, you have it right in front of you. You have your chart there. I'm not going to give you a chart that's like 20 things on it. We're going to keep them reasonable. We're going to find a way at the end of this chapter to see what do we do when it's like 100. What do? We have a special way to find that. The cumulative button says, the reason we don't really use this is the cumulative says this. I'll show it to you. If you do 7 trials, get your probability in here, 0.46. If I want to do 0 and 1, so I want to say at most 1, the probability of getting at most 1 yes. I want the 0 and the 1. So I come down here and I just accumulate up to the 1. It does an at most. So when I do this, it's the same as if I added these 2 up. Accumulating means it does up to that one. You could use it for the at least. For the at least, I could do at most 3. I could do this part here and then subtract it from 1. Do you see what I'm saying? If you want to use a cumulative, just think of it as it keeps accumulating. You know when we made a table and we did the cumulative column? It just keeps accumulating it. That's what this one does. So if I wanted to do the at least 4, I could take these and add these up. Or I could say, okay, let me do accumulate to 3. I'll accumulate it to 3, and then I'll subtract it from 1. So I can do this one, do my trials, accumulate it to 3, and then I'm just going to take that answer and subtract it from 1. So there's a number of ways you can do this. And you can do that. That will add up to what those added up to. So there's a way to do it. I wouldn't use it for that. If you got a net most and you're just accumulating up to that, I would. At least I'd probably just punch them all in. Just because you want to make sure you don't have any overlap there. If you miss the wrong one, you're going to have an overlap. So either way you want to use that, the cumulative is nice, but the PDF one, you let yourself think about binomial. I'm looking for a word that says binomial. I'm looking for a probability distribution function because that's what I have to make right here is a probability distribution function. PDF, that's what it stands for. If you hit VARS by accident, there's not remotely anything that you need there. If you even scroll to the YVARS, still remotely nothing that you need there. If you hit the word statistics, you're not going to find anything that says binomial. So it's kind of like keep trying and you'll hit it with this one. As soon as you see this, you see the normal PDF, you know you're on the right track. Just don't use normal PDF. We're going to use that for something else. We actually use a lot of these by the time we complete this course. We use a lot of these from the calculator. This is really a calculator-driven course. Questions at all? All right. This is giving me grief today. All right, now you guys are going to try this. You're going to do the same thing. What happened when we did this? Where did these probabilities look very, very different than these probabilities. Look what's happening. Where are my biggest probabilities? Up front. Where are my biggest probabilities here? In the middle. Why? Why is this different? Look at how tiny, tiny, tiny these are. These are kind of small. Yeah, but not as small. These are almost as small as my top ones. They're not like minuscules. This is like barely there. Why are they different? What's it saying to you that 0 people said yes on the tablet? Why is that a stronger probability than 0 people saying yes on the cell phone? Because there's far less of them. I would expect less people to say 0 on the tablet, wouldn't I? What is the percentage that they're going to say yes? Only 16%. There's only a 16% chance that they're going to say yes. So therefore, most of them are going to answer me no. So the fact that I get zeros, yeah, that's a higher probability. I get 0 people out of 7 that are going to say yes. I would expect that because it's such a low probability that they will say yes. So this one, I want you to be able to see this. This 0.46, isn't this close to half the people? So look at my curve. It was almost like a normal looking curve, if you will. Like if you kind of like turn this around, doesn't the bars like over on in the front end and the back almost look the same? In the middle is where the lump would be if I graph this. Wouldn't that be like my distribution? It would kind of go like this. My biggest ones are here. My ends both almost are the same. This one's a little different. This one's very skewed. It's higher up front and very, very low over here. I wouldn't have expected that. But if I look at the probabilities, you got to have a backwards look to this. I would expect more people to say 0 because the probability that they're going to say yes, they're going to say no to me. Because the probability that they're going to say yes is so small. So I am going to get some in here that are going to say yes, but not a whole lot. Do you see why those probabilities look so different? Does anybody not see that part? Like, I don't expect you to guess what's going to happen to it. We can certainly just do the math and we can look for it. But I want you to make sense out of why this is happening. Why are my probabilities coming out higher in certain places? What's causing that is the probability of them saying yes. The more people that say yes, if this probability, let me ask you this. If this probability went to 0.86, where would my highest numbers be? Would they be 0 to 2, 3 to 5, 6 to 7? 6 to 7, because shouldn't I expect more people since the probability of them saying yes is pretty high? I would expect more people to say yes because the probability that they will say yes is pretty high. Right? So that's why your probability tables look a little bit strange. Good. Guys, are you sleeping on me or what? Okay. Anybody not comfortable yet with doing this? Okay, so now, example 4. I showed you how to find a cumulative, how to find the exact. I don't have to do that when I don't. Okay. Let's do one more together. Example 5. I don't like to bore you to death, but I know there's people out there that are just not catching this. All right, so let's try one more together. A survey of U.S. adults found that 62% of women believe there is a link between playing violent video games, and teens exhibiting violent behavior. Okay? Now, this is on page 206. See the source in blue? This is a valid source. This was done professionally. Okay? So, most of the times you're getting good data to work with. You randomly select 4 U.S. women and you ask them whether they believe if there's a link between playing violent video games and teens exhibiting violent behavior. You want to find the probability that exactly 2 of them said yes, at least 2, fewer than 2. So we're going to start building your table. So first, let's make sure that this is in fact binomial. So we're going to start with N, P, Q, S. So what's the N? I want 4 people. What's the probability? What's the probability that they will say yes, they find a link? 62%. This is going to say yes. And how many are going to say no? What percent? 1 minus this. So 38%. And the X, I only have to do this 4 times. 0, 1, 2, 3, 4. Because I get no yeses on this. 0 yeses. That's what my 0 means. 0 yeses. So I'm going to fill up my table. Okay, before we do this, where do you expect your larger numbers to fall? Where would you guess them to fall? Your larger percentages? Between 3 and 4, maybe 2 and 3, so towards the bottom, 3 and 4. Why is that, Sarah?
Because more than half of them say yes.
Good, because the probability that they'll say yes is greater than 50%. Good, it's greater than 0.5. Okay, so that's what we're looking for here. We want to see where am I getting this from? Like, what do I expect from this? So again, you're going to do your normal PDF. I'm just going to pull this back down and change this. You have only 4 trials, 4 people to ask. Your percent was 62, and you're going to start at your 0. Can everybody find this one? Everybody can do this. Okay. So again, give me 3 decimal places. I like 3 because I like to look at them as percentages, because 0.021, we don't even say that correctly. We just say 0.021. Technically, it's like 2.1% chance that 0 people will say yes. So I like to look at it as a percent sometimes. So give me that extra decimal. I'm going to do the 1. Okay, I can see it getting bigger. Do the 2. Should it get bigger? Yep, because my percentage is pretty high. 0.333. Pretty good. We've been like this all day. Such weird things happening to my board. 362. 1 more. A 4. At 148. So now, where is my skew? Is my skew? Think about drawing this as a graph. Is my skew to the left or to the right? Where's my small numbers? If I graph this, aren't my higher numbers going to be over here? Where's my lower numbers? It's skewed to the lower numbers. It's going to be skewed to the left. Okay? I expect my smaller numbers to be here. Like Sarah said, my probability is high. I expect them to say, a lot more people will say yes. Okay, so now, let's use our chart and answer these questions. What is the probability that exactly 2 of them say yes? 0.333. I go right to my chart. 0.333. Exactly 2. What is the probability that at least 2 say yes? So what am I looking for? 2 or more, 3 or 4. And what am I going to do with these guys? Add them up. Look at how much of your probability is there. So where most of your probability is. Let's see if I have the answer to this. 0.843. What's the probability that's fewer than 2? What is fewer than 2? Is what? 1 or 0. Good. Now, all I want this time are these 2. I have 2 ways to do this. Can anybody tell me one way to do it? Add them. So I add them together, and I get 0.157. 157. What's another way I could have done that? Subtract. Isn't it everything but this up there? I could do 1 minus 0.843. So we took everything off your chart to find all the probabilities. Not so bad, right? Okay. So we'll call this a day today.